So direct current, or DC, flows in one direction only. The electrons move from a negative terminal of a power source through the circuit back to the positive terminal. It's always constant, always steady, one way, always. So if you plot DC voltage against time on a graph, you'll get a flat horizontal line. The voltage does not change. It's constant at whatever the source provides. So if you have a AA battery with 1.5 volts, that's your voltage. 12 volts from a car battery, that's going to be your voltage. Or, a certain voltage from a fuel cell stack or solar cell panel, that'll be your voltage. So a battery produces direct current. A fuel cell produces direct current. Solar panel produces direct current. All these devices, the chemical or photovoltaic process that generates the electricity, drives the electrons in one constant, consistent direction. Alternating current, or AC, is fundamentally different. Instead of flowing in one direction, AC reverses the direction periodically. So if you plot AC voltage against time, you don't get a flat line like direct current. You get a sinusoidal wave. So this is a smooth curve that rises to a positive peak, falls back through zero, continues to a negative peak, and then rises back to zero again. This cycle repeats itself continuously. So in the United States, the household current completes this cycle at 60 times per second, so it's 60 hertz. In most of the rest of the world, this cycle occurs at 50 cycles per second, so 50 hertz. So the peak voltage of US household current is about 170 volts, but because the voltage is constantly rising and falling, it actually spends a lot of time near zero, and the effective voltage that does the useful work is lower than the peak. And this is called RMS voltage, root mean square. The households in the United States, it's 120 volts. So this is the number you see on your appliances and outlets. In Europe, the RMS voltage is 230 volts. So here's a useful way to picture the difference between AC and DC. DC is like water flowing steadily through a pipe in one direction continuously. The pressure is constant, the flow is constant, and it's predictable. It's the exact same flow rate. AC, the water in the pipe is being pushed back and forth by a crank connected to a piston. It's like the water sloshing rapidly at 50 or 60 cycles per second. The water never actually travels from one end of the pipe to the other. It just oscillates back and forth very rapidly. So the pressure alternates between positive and negative with each piston stroke. So that back and forth motion sounds really inefficient. So why did Tesla champion AC over DC? The answer lies in transformers. And the physics of how transformers work is the key to understanding the war of the currents. A transformer consists of two coils of wire called the primary and secondary windings, and they're wrapped around a shared iron core. So when alternating current flows through the primary winding, it creates a constantly changing magnetic field and induces a voltage in the secondary winding. And the ratio of the voltage induced depends on the ratio of the number of actual turns in each coil. So if the secondary winding has 10 times as many turns as the primary, the output voltage is actually 10 times higher than the input voltage. This is called a step-up transformer. If the secondary winding has 1/10 of the turns, the output voltage is 1/10 of the input. This is called a step-down transformer, and this only works with alternating current. A transformer requires a constantly changing magnetic field to induce the voltage in the secondary coil. So DC produces a static magnetic field, which induces no voltage in the secondary. So it can't be transformed efficiently with a simple electromagnetic induction.